Hi, my name is Olivia Lanes, and today I am thrilled to introduce a new series called Quantum Paper Review. Today we are going to be talking about the paper called The Evidence for the Utility of Quantum Computing Before Fault Tolerance. So this paper was published back in June of this year, and it immediately made waves in the quantum community. The paper stated that IBM researchers were able to simulate an Ising model, which is a model that simulates atomic spins on a chain or lattice on a 127-qubit superconducting system. They were able to measure accurate expectation values for circuit volumes at a scale beyond brute force classical computation. In essence, this ushers in a new era of quantum computing, one where we can find utility for these noisy machines before we achieve fault tolerance. We sat down with two of the authors of this paper. First, we will talk to Dr. Abhinav Khandala, the PI, about the point of this paper, some of the questions that emerged following its publication, and future outlooks. Later, we will talk to Dr. Youngsuk Kim, the first author of the paper, on what it took to publish a paper of this magnitude and some scientific details. Here's my interview with Abhinav. Thank you for stopping by, Abhinav, and congratulations to you as well. Could you first walk me through the title of the paper, The Evidence for the Utility of Quantum Computing Before Fault Tolerance?
Right. Thanks for having me. And the title for this paper was something we deliberated upon quite a bit with both internally and with our collaborators at UC Berkeley. And it's something that we felt really described the essence of what we were trying to say with this work. And maybe it's useful to parse through it a bit.
Mm-hmm.
This is evidence for, and why evidence? Because this isn't quite an open and shut case. There is evidence in the form of experimental data, and perhaps in light of recent classical simulations, I would argue increasingly compelling evidence. And evidence for what? Evidence that quantum computers today could be a tool to access observables, perform computations reliably at a scale that's beyond direct classical simulation methods.
Got it.
Right? And this can be done with quantum computers today in the absence of error correction already, and hence the before fault tolerance. So that's what we were trying to capture in the title.
And what was your specific role in the paper? Because I know you're an experimentalist. We have a similar background. So what did you actually do?
Right. So on this paper, I am the PI.
Mm-hmm.
And so in addition to the science, which has been a very interesting journey, as I said, a culmination of over 6 to 7 years of work with Kristen, Jay, and Sergey pushing along this thread of error mitigation. And beyond the science of it, it's also trying to assemble together, a team of very motivated, smart people.
So you're the glue.
Well, that's too much credit, but yeah, it is. They're trying to have the right team together, trying to get the resources to run an experiment at this scale,
mm-hmm.
trying to coordinate these efforts with our collaborators at Berkeley. That's also part of the things I had to do for this.
Got it. Can you describe a little bit in more detail what problem was addressed?
Right. So essentially, we're looking at an interacting spin system,
mm-hmm.
And it's referred to as an Ising system. This is a very well-studied model in physics and connects to many different phenomena across various areas. And essentially, we're trying to ask the question, when we have this interacting spin system and we begin to suddenly turn on certain interactions, how do properties of the system evolve in time? Properties such as the global magnetization, the global spin of the full network, how does that evolve? We're trying to answer questions like that, mm-hmm. And trying to get a sense of as we look at increasingly complex properties of this evolution, is the quantum computer able to keep up and continue to produce reliable results?
And what is the main thesis of the paper? What is the significance of the idea of finding utility?
Right. So what is a really, really pressing question today in the entire community is there anything useful one can do with an existing noisy quantum computer
Yep.
or near-term quantum computers even before the advent of full error correction? And this is really the first piece of experimental evidence that seems to suggest that this might be a possibility. And what we essentially have now is basically a tool, a scientific tool where we can run computations that are beyond the scale of what one can access with direct classical simulation. And one has had a wide range of near-term quantum algorithms that have been proposed
Right.
that have never been tested at this scale. And now you have this foundational tool to really go and explore these different algorithms and really see if there are near-term quantum applications that we can access even before one has error correction.
Right. And I like what you said about the scale, because it's not like people haven't attempted this type of methodology before. It was just on much smaller scale devices where we knew what the answer would be from checking it classically, right?
Right. And that continues to be something that's of most importance even at this scale. And that's why a large emphasis of this work, even when you're running experiments with this large number of qubits, is to even understand, well, are these methods, is the device working in exactly verifiable regimes? There are special test cases you can work with, even with a large number of qubits, where you still know what the right answer is. And that is the essence of what this experiment is trying to still do. Mm-hmm. But yes, as you said, there has been this very interesting evolution over the last 5 or 6 years, scaling from very small, the initial ideas of error mitigation, to the initial experiments with 4 qubits, now scaling up to 127. And a lot of this development has been going hand in hand with what we've been able to do with our quantum hardware progress as well.
So in your opinion, what is the most important figure in the paper? And could you walk me through it? Could you walk the audience through it, assuming that maybe they haven't read it yet?
Yeah. So perhaps if you asked this question to me a few weeks ago, I might have said it was figure 3, which is really looking at increasingly complex observables on this very large circuit that we've run, at this very non-trivial scale, but still in regimes where we know what the right answer is, and showing that even as we're increasing the complexity of the quantities we're measuring, the quantum computer is still able to provide reliable results, right? And now in the absence of any error correction.
Right.
This was hands down the most important figure for me.
But now you changed your mind?
Perhaps, because what we also did was we tried to push beyond exact verification, right? We tried to push the circuit to an even longer depth, and there was, like, even though we published the data, there was still some nervousness on my end. Is this really correct?
Sure.
Right?
That's natural.
Yeah. So there was a very clear deviation with the classical approximate methods that we showed. And one question for me was, well, is it just that the experimental data is decaying much faster because there's too much noise, because the circuit's gotten larger and so on? And then, very interestingly, what we've seen over the last few weeks is that there've been a host of different classical simulation methods coming from leading groups across the world, trying to benchmark this data. And they all disagree by about 20% with each other.
They disagree with the classical methods.
They disagree with each other by about 20%. And the experimental data lies within that uncertainty. And in the absence of an exact answer, we don't know what the exact answer is. You have all of these classical approximations which disagree with each other. And then in that, now you have points from a quantum computer. That to me is very compelling evidence that we now have a new scientific tool, right?
Right.
So now I might lean on the sense of, maybe 4B is the most interesting piece of experimental data coming. But yeah, I think this is a very fascinating time.
So I guess actually this leads me to another question.
Yeah.
You said we don't know what the answer is, but when we have, a quantum computer that says, the answer is this, and we have a classical computer that says the answer is this, what do we do? How do we know which one is more correct?
Right, and this is a very interesting question, and this is something, how this evolves is is going to be very interesting. One might have to invest more classical resources to get a better approximation. And this is why it's also very important to use classical approximations that are controllable and have guaranteed convergences. But also, as quantum hardware gets better, running the same experiment on an improved quantum system might be another way of verification. In more general cases where one's say interested in simulating properties of molecules, for instance, perhaps one could actually go and measure what the dissociation energy.
That's what I would have thought. Like,
right.
We don't know the answer. Let's just do it in the lab and see what happens.
Okay,
and
right.
Nature will tell us what method is right.
Exactly. And that's also one way this kind of debate would could go forward. But this is a very interesting time.
Yeah, I mean that's a whole new territory.
Yeah.
And I think that's what the paper is really getting at, right? Like, this is a new era.
Yes. This is a new tool with which we can basically try and address questions like this.
Got it. And from this paper, did we learn anything that's generalizable to other work that we want to do and other experiments? Yeah,
this is a question that I get a lot. Well, is the utility lying in the fact that you try to simulate a physical model, you try to do a simulation of what's referred to as an Ising spin system, and the answer is no. Well, this was just an example of what we did, but really the essence is we're trying to take a short depth quantum circuit, and we're trying to estimate properties of the state we're preparing with that circuit. Okay, and these properties are referred to as expectation values, and this is the core primitive of a vast number of near-term quantum algorithms. If one wanted to run a variational quantum eigensolver to estimate binding energies for molecules, this is the kind of thing you measure. If you wanted to measure a kernel estimation algorithm for machine learning, this is the kind of primitive you rely on. If you were trying to measure magnetizations or other correlation functions for interacting many-body systems, these are the kind of quantities you want to measure, right? So for all of these, the essence comes down to taking a short depth quantum circuit. The depth is defined by the amount of noise in your quantum system, and then trying to measure these expectation values at the end of it. And we're showing that with error mitigation, there is a path to accessing these accurately, reliably, even without full-blown error correction.
Got it. What's next for this type of experiment? Are you taking the work any further?
Yeah, that's a great question. So I anticipate there will be this increasing back and forth between classical and quantum. There's been a lot of interest on the classical simulation side already.
Yeah.
And the very nature of these approximate classical techniques is they will inform us about regimes where some of these methods might struggle. And that will kind of tell us where the interesting circuits lie. What are the kind of interesting circuits? This wasn't the emphasis of this work, but really trying to understand what are the circuits we want to run. What are the kind of observables we want to run, right?
Right.
And I think with this tool, with the 100 by 100 challenge, working with these working groups, we're really hoping to collaborate with a wide range of our partners to tell us what are those interesting problems, what are those interesting circuits to run on these systems with this tool. And while this back and forth with classical methods and quantum is going on, I think there's going to be a lot of progress on both ends. The classical methods will continue to evolve, and there will be very nice advances on that end as well. And even on the quantum, if we just compare to the state-of-the-art metrics we have, there is perhaps an order of magnitude improvement in coherence and gate fidelity to be made use of, compared to the already state-of-the-art device that we had used for this experiment, right? So all of this is going to enable even more complex circuits, even more circuit depth, circuit volumes, and this will just make this back and forth even more interesting. So this is something I'm very much looking forward to as well.
Right. Thank you, Abhinav. That was very illuminating. It makes a lot more sense now.
Thanks.
Next, we will be talking with Dr. Youngsuk Kim, the first author of the Nature paper, which is typically the person who's responsible for the majority of the work, in order to get a sense of some of the experimental details, error mitigation, and future experiments. Here's Youngsuk. So I have some questions about the paper that are personally interesting to me, but I also think might be interesting and important for our community and our researchers to know. And I know you've done a lot of interviews already about this paper, but I'm hoping that this one will be a little bit different because I'd also really like to get your insight on what it takes to actually publish a paper of this magnitude. So what was your specific role to write this paper?
Yeah, so my role is maintain the device up and running in an optimal condition.
Yeah.
So I ran the circuit and we tested out this error mitigation technique at this scale. So you may notice there are a lot of authors in this paper, and some of them are doing similar job with me. I brought up this device with them. But it's really not just these authors' job that enable this device. It's whole IBM's team's job.
Right.
There are like many people actually acknowledge it in this paper. You can find in the paper.
Right. It was a huge team effort.
Right. It's a huge team effort.
What does this tell us about the actual device that we were able to use for the paper?
Right. So it is non-trivial work to scale the device. Like if we look at the historically, like 5 qubit, 27 qubit, 65 qubit, 127 qubit. So each individual qubit performance is definitely different when it comes to a lot of integration and things getting to 127 qubit level. So this paper is also showing that all the integrations, like device integration, new design, freeze, and room temperature electronics, all put together works at this scale.
Right. So it's really like a huge win, not just for the software and the theory, but for the engineering and the physics that went into building the hardware as well.
Right.
Got it. Got it. How long did it take you guys to write the paper and gather all the data for the paper? Like, surely you guys had to run, thousands of circuits.
So if you just naively count how many circuits
Yeah.
we ran for this paper, it's almost like 100,000 circuits.
It's a lot.
Yeah, that's a lot of circuit. So if I think about when this work is really started, we can go all the way back to 2017. One of the paper that Abhinav wrote. It was just like 4 qubit depth 2 circuit, calculating molecular energy, ground state energy. There, they realized that the answer we get is noisy. So is there any way to improve this? So then they start to think about this error mitigation method, and 2019 they actually demonstrate this error mitigation method.
Right, that was the first error mitigation paper, right?
Right. So that's a zero noise extrapolation, which is the method that we used. And then they are thinking to scale this up. We first visit our Falcon device, 27 qubit device, and there we use 26 qubit. And we kind of test out what kinds of problem we will have when we scale this out, actually. You can say, it takes like 5+ years or something. But the actual paper itself almost take like a year or so.
Gotcha. Okay. You mentioned zero noise extrapolation, but I'm not sure everyone knows what that is. So in your own words, what is zero noise extrapolation?
Yeah, so zero noise extrapolation is one of the error mitigation methods proposed by IBM and Oxford. By measuring some noisy observable, and if we have a magic handle to globally scale the noise and make our observable a little bit more noisy, and by watching this trend and extrapolating out of it to zero noise limit, we can get zero noise limit expectation value.
So you make the noise worse on purpose,
Right.
so you can predict what the observable would look like with no noise.
Right.
Interesting. Okay. What specific challenges, like what was the hardest part about, you mentioned the experimental work, the room temperature electronics, running 100,000 circuits. What was the hardest challenge you had to overcome?
So I think there are like a lot of challenges.
Yeah.
First of all, it's almost first time, at least for me, to run this complicated circuit at this scale. So there are a lot of challenges popped up in the middle. For instance, This type of job is this type of job consists of many random circuits. We quickly realized that there's a lot of classical overhead we have to pay when each of these random circuit gets submitted. So that's some challenge that we identified, and we are really active in addressing that. And that's I can call it as a classical overhead.
Yeah.
So classical overhead is definitely something we identified as one of the biggest challenge. The other one is the quantum device part. So when it comes to this scale, it's first of all very hard to calibrate the device.
Yeah.
So there has been a lot of know-how and calibration technique accumulated, and we practiced until like all the devices like 5 qubit, 27, 65. So all those knowledge transferred to 127 to enable this. So it was very fortunate for us that we have those like background and experience and knowledge, all that ready for this one.
Right.
So that is very challenging, but we addressed that. And another challenge we identified during this work was the stability of the device.
Oh, interesting.
So it is very well known that the superconducting qubit is unexpectedly interacting with background, right? And this background interaction comes and goes, and it kind of introduces additional stability issue.
Yeah.
How to deal with this? Eventually, we want to deal with this in a hardware fashion, maybe, but with current given resources, how to address that was also very challenging.
I think this is really interesting because obviously when you write a paper, there are page limits. You can't write about every single thing that you learned in the paper.
Right.
But what I'm hearing from you now is that the amount of stuff that we learned from trying to write the paper for this experiment was like exponentially larger than what actually ended up in the paper.
Right. So yeah, we have a nice discussion in supplementary material as well.
The supplement is where you always find the good stuff.
Yeah.
So what, in your opinion, is the most important figure in the paper? And what is the figure telling us?
Right. So so figure 1 is schematic. Figure 2 is some check. And figure 3 is, I found, the most interesting figure in our paper.
Okay.
Figure 3 is definitely basically exploring different circuit limit. Some limit that is really easy for classical computer to simulate, and the other limit which becomes a little bit more tricky to get some brute force manner answer. Figure 3 is basically illustrating that throughout all those regime, quantum computer is producing reasonable answers. Whereas some of the classical pure approximation method may struggle.
Right. And that's really where the utility comes from, that region where the classical computers are struggling.
Right.
And the quantum one is still producing pretty accurate measurements.
Right.
Got it. So what are the limitations to your findings in this work?
Yeah, so this error mitigation scheme works in a way that we obtain noise observable and post-process it. So that means when our circuit gets deeper and deeper, our noise observable, the signal gets weaker and weaker. So it's more and more challenging to mitigate out of this very noisy signal. So it'll get better as we develop better device, improve coherence and gate fidelity, something like that.
Right, which is still, of course, a priority.
Right. And another aspect of this particular error mitigation method is that it may struggle for some very complex observable for some very similar reason that I mentioned just before. But there's a more powerful error mitigation technique. But of course, there's no free lunch. It tends to have more overhead.
Right.
So as our device get better, we can think about using more powerful error mitigation technique to address some of those issues.
Gotcha. So what we've learned from this experiment is that there are certain error mitigation techniques which can lead to utility. And in what other ways is what we've learned generalizable to other experiments?
Yeah, so these error mitigation techniques are basically working around measuring observable in short depth circuit. So in fact, there are many other applications using these kinds of primitive, right? Measuring observable in short depth circuit, such as optimization problem. Like for instance, calculating ground state of the chemical chemistry, some molecular energy, also some machine learning techniques using some kernels. So you can generalize to other type of applications that is using this kind of primitive.
Cool, awesome. Thank you so much for coming in, Young-Suk. I really, really appreciate it. And thank you for answering all of my questions very thoroughly.
Thank you. Thank you, Olivia.
Thanks again to Abhinav and Young-Suk for visiting us in the studio and answering our many questions about the utility paper. If you haven't seen or read the paper yet, check it out in the description below. If you have questions or a paper that you would like us to review, let us know in the comments. See you next time.